NES Tetris starts to act really weird if you can manage to get to really high levels. First, at level 29, the pieces reach a top speed and will never drop any faster. If you get to level 30, the level number display starts to show the wrong number. Then at level 138, the colors start to glitch out. Starting at level 155, clearing a line has a chance to crash the game. And then at level 160, random glitchy tiles may start appearing all over the screen once in a while. How can such a simple falling block game mess up so badly? We'll have to take a deep dive into the code to figure out, so buckle up. Retro Game Mechanics Explained is brought to you by its YouTube members, Patreon supporters, and viewers like you. Thank you. Let's look into these one at a time, in the order that you would run into them during a long play session. The first of these is the Tetramino falling speed limit that you hit in level 29. Out of all of these 5 quirks, this is the only one that was intentionally coded into the game. Here's the bit of code that is responsible for checking if a piece should move down on a given frame. Let's take a look at the variables used. First is this counter we'll call fall timer. This is just a generic counter that counts up once per frame. It is used to keep track of how many frames a piece will hover at a specific Y position before falling down one row. The number of frames a piece will hover is determined by the values in the table over here, labeled frames per drop table. This is a list of frame delay counts for each level, from 0 up to 31. For example, on level 0, it takes 48 frames for each Tetramino to fall down one row. On level 1, it takes 43 frames, level 2, it takes 38, and so on. Then at the end here, on level 28, it takes only 2 frames for a piece to fall. On levels 29, 30, and 31, this table says that it should only take a single frame, the fastest a piece can fall. This table is found in the game's ROM, but the current falling delay is copied into RAM at this location named drop speed here. Then down here, there is also a memory location used to store the current piece's Y position in the board. At an earlier point in the game's code, the piece's fall timer is incremented by 1. This always happens as the Tetramino is falling in the board. Later on, the game checks if the current level number is 29 or greater. If it is 29 or higher, then this default frame delay of 1 is used. In this case, the frames per drop table is never referenced at all. This means those 3 1s in the table are pretty much useless, since they aren't even read at all. If the current level is 28 or lower, then the game will fetch the corresponding frame delay from the table in the ROM. This value, or the default 1, is copied to the RAM address drop speed. Then, this threshold is compared with the current counter value. If the counter is equal or greater than the frame delay, then it is determined that it is time for the piece to fall down one row. Otherwise, the code exits right here. To move the piece down a row, a bunch of stuff happens, but the only important stuff here is that the fall timer is reset to 0, and the Y position of the Tetramino is incremented by 1. This code continues to function correctly as the level increases all the way to 255, since this compare instruction right here is able to successfully detect if the current level is greater than or equal to 29, no matter what the level number is. Don't get used to this, however, since this pattern will not hold as we look into the next few things. If you get past level 29, you'll level up to level 30. But the level number at the bottom right of the screen will display 0 for some reason. This one is actually pretty simple, but it requires us to know what binary coded decimal is. The level number is stored in RAM as a standard 8-bit byte. This means as the level goes up by 1, the level number byte is incremented by 1. We can express this in terms of binary and in terms of decimal, but we can also express this in terms of hexadecimal. Notice that when we hit level 10, the hexadecimal representation becomes hex OA, and level 16 is hex 10. This is just how hexadecimal works. The second digit from the right counts in 16s rather than 10s. Now, the level number display on screen is 2 digits wide. We could dedicate a separate byte for each digit, but that would kind of be a waste of space. Besides, a single byte can hold 256 different values, so that should be able to hold all of the level numbers we could ever need. However, since the game wants to display the level number in base 10, it has to convert it from binary to decimal. This is kind of a pain, but there's a different, better way it could be done, and this is where binary coded decimal comes in. Instead of treating the entire 8-bit byte as one number, we can split the byte into 2 halves and treat each of the 4-bit nibbles as 1 digit each. So in this case, the lower 4 bits become the ones digit of the level number, and the upper 4 bits become the tens digit. We can count up in binary coded decimal just as easily, but it just requires us to make an adjustment when we go from 9 to 10. Instead of making the lower digit binary 1010, we reset it back to 0 and increment the upper digit. Now, if you treat these 2 half bytes as a whole 8-bit byte again, it will look like we jumped from 9 to 16. But if you look at the hexadecimal representation, it looks like we're counting up in decimal. This format turns out to be really handy when updating tiles to draw to the screen, because the game can easily convert these 4-bit nibbles into tile IDs that it needs to display. However, there is one critical step that needs to occur for all of this to work. Since the level number is stored in a standard binary format, it needs to be converted into binary coded decimal format. This can be done with a simple lookup table, of which there is one in the game's ROM. However, this lookup table only holds values from 0 to 29. So if you try to look up what 30 should be in binary coded decimal, you'll exceed the boundaries of the table and start to read garbage data. The data that follows this lookup table in the ROM is actually another lookup table that just holds the multiples of 10 to help speed up various calculations. These are standard binary numbers and not in the binary coded decimal format, so the raw hexadecimal representation of these numbers end up being used as the level numbers once you get past level 29. So level 30 becomes hex 00, 31 is hex 0A, 32 is hex 14, and so on. When you hit level 138, suddenly the standard rotation of color palettes breaks, and the board becomes a very odd mix of colors. Even further levels result in some glitchy-looking colors. But what could cause this? Let's look into the code that handles updating the color palette of the board when you level up. There's this chunk of code that does all of the updating, but accompanying it is this table of 40 bytes that just defines each of the colors for each color palette. There are 10 sets of 4, since each palette uses 4 colors. The first color is effectively ignored since it is substituted with transparency for the moving sprites, and the second color just happens to always be defined as white for every level. When you get to level 10, the colors just repeat over and over again. Level 10 shares colors with level 0, level 1 has the same colors as level 11, 21, 31, and so on. In the code here, it's clearly referencing the level number memory address here, but it uses a few more memory locations down here. Let's see. In order to change a color in the palette memory of the PPU, the CPU needs to write 3 separate bytes to specific memory locations. The first 2 bytes need to be the 16-bit address in video RAM where the certain color you want to change is located. Palette memory spans from hex 3F00 to 3F1F in video RAM, 1 byte for each of 32 colors, so your 16-bit address will always fall within this range. The location the CPU needs to write this address is in this PPU ADDR register. In order to write the full 16-bit value, the upper 8 bits are written first, then the lower 8 bits are written to the exact same register. Then the third byte is just the ID of the color you want to use. This gets written to the PPU data register. As a convenience, if multiple color values need to be written, you don't need to write the VRAM address every time. The PPU ADDR register is internally automatically incremented every time PPU data is written to. So as long as the colors are contiguous in memory, you can just keep writing to PPU data over and over again, and it will transfer the data to video RAM just fine. That's essentially what this code is doing. First, it looks at the level and compares it to the constant 10. There are only 10 different color palettes, so this part is looking to constrain the level number between 0 and 9, so we can use it as an index into the color table. What it would like to do is repeatedly subtract 10 from the level number until it becomes less than 10. The result would be the palette index to use. For example, level 24 is greater than 10, so it subtracts 10 to get 14. This is still greater than 10, so it subtracts 10 more to get 4, which means level 24 will use palette index 4. However, this BMI branching instruction doesn't quite do what it was intended to do if we consider that the level number can go all the way up to 255. A CMP instruction, short for compare, is really just a subtraction instruction in disguise. So here, 10 is subtracted from the level number. The BMI branch instruction will essentially look at the result of that subtraction and branch if the result is negative. So reiterating the example we did earlier for level 24, the CMP subtracts 10 from 24 to get 14. This is not negative, so the following subtraction instructions execute, which is a true subtraction that actually modifies the underlying value. So we jump back up and do another compare. This time, 10 is subtracted from 14 to get 4. This is still not negative, so that 10 gets subtracted off for real, and we jump back up a second time. The third time, though, the CMP will subtract 10 from 4 to get negative 6. Since this is negative, the BMI will branch forward, and we remain with a value of 4 in the accumulator. However, the big mistake here is the type of branch instruction used. BMI stands for branch if minus, which effectively can be thought of as a branch if less than instruction. However, this only works for signed bytes. If the result of a previous comparison is less than 0, that is, between negative 128 and negative 1 inclusive, the branch will be taken. Otherwise, if the result is between 0 and positive 127, the branch will not be taken. This can cause problems with comparisons that check if a certain value is negative, since some values that are positive when treated as an unsigned byte are negative when treated as a signed byte. For example, unsigned 8-bit 128 is the same as signed 8-bit negative 128, and unsigned 8-bit 255 is the same as signed 8-bit negative 1. The level number is being compared here as if it were a signed byte, while the structure of this code is treating it as an unsigned byte. This first causes an issue at level 138. Let's look at level 137 first, though. The CPU loads in the level number of 137 and executes the CMP10. This subtracts 10 from 137 to get 127. The BMI instruction recognizes that this is a positive number. In fact, 127 is the highest possible 8-bit signed value. The branch is not taken, so the level number gets reduced to 7 after a bunch of repeated subtractions. For level 138, however, the CPU loads in the level number 138 and executes the CMP10. This subtracts 10 from 138 to get 128. As a signed 8-bit number, however, this is treated as negative 128. This means the BMI branch if minus instruction sees this as a negative number and will take the branch. As a result, the code that follows will receive a value of 138 instead of a number between 0 and 9 as expected. Let's take a look at this code right now. The incoming value is multiplied by 4 since each of the palettes is 4 bytes wide. This calculates the offset of the first color of the intended palette in the big table. These would appear at multiples of 4, so 0, 4, 8, etc. The unintended value of 138 gets multiplied by 4 and truncated to 40 since we're still limited to 8 bits here. Next, the game sets up the VRAM address of those colors that it wants to update. The high 8 bits of this pointer are always hex 3F, so that is hard-coded into this LDA instruction. But the low byte does change, so that is temporarily stored in this palette pointer low location. The way that it prepares this pointer to be written to the PPU ADDR register is kind of convoluted, and it isn't super important for our understanding of how the glitched colors happen. But in short, there are 8 sets of 4 color palettes used in the NES, 4 for the background and 4 for the objects. The colors for the board are written in 2 places, one for the background stack and one for the object currently moving in next pieces. These palettes are at addresses hex 3F08 and 3F18 respectively. This part of the code is written as a loop. On the first iteration it writes those for the background, and on the second iteration it does it for the objects. After the address is written to PPU ADDR, the 4 entries in the palette table are written to PPU data sequentially. On level 9, our base index becomes 9 times 4, or 36, and the indices 36, 37, 38, and 39 are copied to VRAM. Index 39 is the last entry in this table. But with level 138, the unintended index we end up with is 40, remember? This means this table will be indexed out of bounds, and we start reading values that were never intended to be color IDs. For the next 54 levels, glitched color IDs get copied to VRAM. Then on level 192, it wraps back around to the normal colors again. This is because 192 times 4 is 768, but this gets truncated all the way back to 0 when limited to 8 bits. The standard 10 sets of colors show up in order, but the glitched ones return on level 202, because 202 times 4 is 808, which also truncates to 40, just like 138 did. Understanding how the crashes and glitchy tile confetti work requires a bit more of a backstory on how the NES works. For the majority of the time, the NES's CPU is busy executing code to run the game. At the same time, the NES's PPU is busy generating the video signal that displays on the screen. It reads information from video RAM, so it knows what colors and tiles to use to make this picture. But when the PPU is reading from VRAM, the CPU should not try to access VRAM, since this can cause read and write conflicts. But the CPU is in charge of processing the game's code, so how can it tell the PPU to draw what it needs? If no changes to VRAM are made over time, the PPU will just end up drawing the same picture over and over. Thankfully, there is a short bit of time in between each frame, called the vertical blanking interval, or VBlank, where the PPU gets to take a little break. It is during this time that the CPU is free to make all the changes it needs to video RAM, and it needs to hurry up and do everything it needs to do before VBlank is over. This back and forth exchange of who gets to access VRAM is sort of like the backbone of how graphics work on the NES, and it is important that it works in order for a game to function properly. But how does the NES know exactly when the frame is complete and it is okay for the CPU to start updating VRAM? Well, in addition to the PPU generating the video signal, it will generate an interrupt when it gets to the end of the visible part of the picture on that frame. The CPU will be alerted to this interrupt and will, interrupt its normal flow of execution of code. When the CPU gets an interrupt, it will put down everything it is currently doing and move its program counter to a very specific ROM address. In order for it to go back to where it was before the interrupt, the old program counter is kept track of in the stack, as well as the processor flag bits. But now the CPU will be executing completely different code, what is called the VBlank routine. This routine is intended to be run exactly once per frame, so anything that happens at a constant rate will happen here. It is in this routine that any necessary data gets uploaded to VRAM, and maybe some other stuff, like checking the state of the controllers. When it's finished, it will return from this interrupt, which just restores the program counter to what was saved in the stack, and code execution continues there, as if nothing ever happened. Here's the kicker though. Since this interrupt always happens at the exact end of the frame, the CPU can be busy with any section of code and it will get interrupted. The interrupt waits for nothing. The CPU can be busy doing any code calculation that happens in the entirety of the game. If it receives an interrupt, it will stop what it's doing then and there. This is kind of a problem because what if the CPU is in the middle of a delicate operation? The CPU has 3 general use internal registers, A, X, and Y. The VBlank routine will likely use all 3 of these to do whatever needs to be done for the controller input and VRAM modifications. So what happens to the values held in the A, X, and Y registers during the operation the CPU was in the middle of doing? Well, if care isn't taken, they can easily be overwritten. During this interrupt, the program counter and processor flags are automatically pushed to the stack. This is just a built-in part of the interrupt process. But anything else needs to be saved in software. This is why the first part of the VBlank routine in most games starts with something like this. The first instruction pushes the value in the A register to the stack. The next 2 instructions save the X register, and then finally the next 2 save the Y register. Now that the 3 internal registers' values are safe in the stack, the VBlank routine can use the registers without any worries. At the end of the VBlank routine, we find the exact opposite thing happening. The registers have to be restored via software as well. These happen in reverse order, so the Y register pops off the stack first, then the X register, and then the A register. Then the RTI instruction returns from the interrupt, which restores the program counter and processor flags. Now the code written here makes sure these 3 registers are safe from being overwritten. However, this does not take care of any extra values held in the entirety of work RAM. In order to safely use memory locations in RAM during the VBlank routine, they should either be reserved to only be used in the VBlank routine and nowhere else, or they need to be pushed to the stack, just like the A, X, and Y registers here. For example, if we wanted to be able to use the location hex 69 in memory, we could load in the value in that memory address and push it to the stack. Then we'd just have to do the reverse at the end of the VBlank routine. This way, if the code the CPU is running before the interrupt was making use of memory address hex 69, it can be ensured that the original value is preserved and didn't get overwritten at any time. So, making note of all of this, what do you think happens in NES Tetris? Or rather, what doesn't happen? I'll give you some time to think about that. Let's go on a tangent about another bit of code in the game's ROM. There's a useful programming technique that allows you to jump to a number of different code paths depending on a single variable. We saw some branching instructions already, but those only allow for 2 different outcomes. Either the branch is taken, or it isn't. Sometimes it's nice to have more than 2 options for what to execute next. In modern programming languages, this can be done using a switch case block, but in assembly, this is normally implemented using a jump table. Some assembly languages have an instruction that allows you to specify the location of a jump table, and then perform the dynamic jump in one go. However, in 6502 assembly, what the NES uses, there is no such thing, so a jump table implementation had to be done in software. This is the routine that NES Tetris uses to do just this. The closest that the NES can get to a dynamic jump instruction is this one right here. This will jump execution to the 16-bit pointer that is located in memory at address hex 0000 and 0001. So what this code does is copy a particular pointer from within a given jump table and pastes it into memory at location hex 0000 before executing this jump. Let's take a look at this routine in action. Here's a small bit of code that runs very frequently. The game mode memory location holds the ID of what state the game is currently in. 0 corresponds to the copyright screen, 1 for the title screen, 2 for the game settings screen, 3 for the level select screen, 4 for the main game screen, 5 for the attract mode demo, and 6 to initialize the demo mode. Here we have the dynamic jump that will go to one of 7 pointers depending on what the current game mode is. The jump table is located directly after this jump to subroutine instruction. There are 7 16-bit pointers that correspond to these 7 game modes. The JSR instruction is usually meant for calling a subroutine. The program counter will be set to the location specified, and a return instruction will bring it back home at the end of the routine. This is done by saving the old program counter on the stack, not unlike how the interrupt does it. But in this case, the JSR is used as a way of jumping to the dynamic jump routine while also pushing the program counter to the stack. We won't be coming back here after all, but we do need to know where this jump table is located in the ROM, and that program counter is perfect for that. Now, due to how the JSR instruction works, it's going to push the 16-bit pointer of hex 8165 to the stack. First, the high byte of hex 81, then the low byte of hex 65. This jump table is actually located at hex 8166, though. This is just a quirk of the 6502 architecture, so we just have to deal with it being off by 1. Then, the jump is taken to address hex AC82, which is where the dynamic jump routine is located in the ROM. The A register currently holds the game mode index value from before the jump. Right here, that value is multiplied by 2 by shifting the bits left once. This is because each 16-bit pointer in the jump table is 2 bytes wide, very similar to how in the palette example each entry was 4 bytes wide. The indices into the jump table should be 0, 2, 4, and so on for each of the pointers. This gets transferred to the Y register, but then incremented by 1. This is how we get around that off by 1 issue. Since the base pointer we're given in the stack is 1 less than we want, we just offset that here. This means that the indices into the jump table end up being 1, 3, 5, and so on instead. The next couple instructions pull that base pointer off of the stack and stores it temporarily into memory at address hex 00 and 01. This way, the next set of instructions can use it as part of the effective address to load the final pointer from. First, the low byte of the pointer is fetched from the jump table and kept safe in the X register. Then the high byte is fetched. Now that both bytes are fetched from memory, the temporary pointer at address hex 00 is of no use any longer and can be overwritten. So the jump target finally gets stored to those same memory locations, and then the dynamic jump instruction is executed, which will finally get the CPU where it needs to go. So to reiterate, suppose the game is currently on the level select screen, which corresponds to game mode ID of 3. Looking at the jump table, we want to end up at address hex 82D7. First, the value of 3 is loaded into A, and then the JSR will push hex 8165 to the stack, and execution moves over here. That 3 gets multiplied by 2 to get 6, transferred to Y, then incremented to 7. The byte hex 65 gets pulled from the stack and written to memory address hex 00, and hex 81 gets written to address 01. This instruction will load the byte from ROM at address hex 8165 plus 7, or address hex 816C. This is the hex D7 found in the jump table. That goes into the X register, and Y is incremented to 8. Then this instruction loads the byte at hex 8165 plus 8, or hex 816D. This is the hex 82 found in the jump table. That gets directly written to address hex 01, and then the hex D7 gets written to address 0. Then finally, the JMP will jump to the address hex 82D7, since that is what is now in memory at address hex 0000, which is exactly where we wanted to go. So, did you figure out what the game doesn't do during its VBlank routine? The answer is, it doesn't attempt to preserve any memory locations, only the internal CPU registers. While there are a handful of memory locations that are reserved only to be modified by the VBlank routine, there are some that are completely unrestricted. See, the 6502 CPU in the NES only has those 3 general usage registers, A, X, and Y. But a lot of the time you need more than 3 bytes of working space in order to do more complex operations. The only option is to start using bytes of memory too. These types of memory locations are sometimes referred to as scratch RAM, since they aren't really dedicated to a specific purpose and can be used whenever needed. though special care needs to be made not to clobber values in Scratch RAM when they're still intended to be used. This is exactly what NES Tetris didn't do. See this dynamic jump routine? The memory addresses hex 00 and 01 are Scratch RAM addresses. A value is first written to them right here at this instruction, but after the final JMP instruction, the Scratch RAM is said to be free, since they have fulfilled their purpose and now the values can be overwritten if needed. A problem occurs, however, if the CPU gets interrupted sometime within this very small window. The VBlank routine ends up overwriting memory at addresses 00 and 01, even though this dynamic jump routine isn't done using it. This results in the pointer for the dynamic jump to become corrupted. The CPU will end up jumping execution to somewhere completely out of place, and the game ends up crashing as a result. Okay, but if the CPU can be interrupted whenever, why does this not happen, all the time? Let's go back to that balanced exchange of handling video RAM. In between frames, the CPU can access video RAM while the PPU is taking a break. But during the frame, while the PPU is using VRAM to output the image, the CPU is doing its own work, handling all the game functions. Under normal circumstances, the CPU finishes doing all of its work before the PPU is done with the current frame. But the CPU, as a machine, can't just stop executing instructions. Instead, it runs into some code that just repeats itself over and over and over again. This is called a spinning loop, since nothing is happening. Essentially, the CPU is just spinning in place, waiting for that interrupt to eventually fire and break it out of this tight loop. If this is the case, there will never be an issue with the VBlank routine overriding anything, because while the CPU does get interrupted, it is interrupting its lonely spinning loop, which is completely safe. But bad things start to happen if the CPU is so busy on a single frame that it never makes it to the spinning loop in time. This is essentially what causes lag in games. A standard part of any VBlank routine is to first detect if the CPU was sitting in its spinning loop. If it wasn't, then the VBlank routine can just return immediately to give the CPU an entire extra frame to finish what it was doing. However, NES Tetris does not perform this check. For the most part, the game is not very laggy at all, and the CPU is very good about finishing all of its work on time before the frame is done being drawn. This all changes when a player makes it to really high levels, however. This behemoth of a routine is responsible for adding points to the player's score every time a piece locks into place. I'm not going to go as in-depth for this one as I did the other one, but here's the general idea. First, the game checks how many lines were cleared as a result of this piece falling into place. It uses that as an index into this small table, which holds how many points each kind of clear is worth. Then it adds this number to the score. The score is held in 3 separate bytes in binary coded decimal format. While this makes it much easier to convert into tiles for storing into VRAM, it makes it a chore to do arithmetic with it. First, the tens and ones digit of the line clear amount is added to the tens and ones digit of the score. It checks if this caused an overflow into the hundreds place and fixes it if so. Then it takes the thousands and hundreds digits of the line clear amount and adds it to the corresponding digits of the score. Then it checks if this caused an overflow into the thousands place and fixes it if so. It does the same thing for the 10,000s and the 100,000s place. Then finally, it checks if this would cause an overflow into the millions place. If it would, then it just hard caps the score at 999,999. It decrements the counter it made, and then repeats this entire process over and over again. Since the line clear amount is multiplied by what level you are on, plus 1, this means that for higher levels, this loop can run several hundred times. After all of that, the game marks the score to be updated on the screen and exits the routine. It turns out that doing all of this score calculation can take up the majority of the length of a frame if the level is high enough. In fact, at the highest levels, adding in the score for a Tetris can take over a frame, which will guarantee a lag frame every time. Now, if the CPU gets interrupted by the VBlank routine while doing the score calculation, nothing super terrible happens. That's because while this routine does use some scratch RAM, the adding counter variable, and the vblink routine does overwrite this memory, clobbering the variable, all it does in this case is mess up the score calculation, since the loop will not run for the intended number of times. Sure, the amount of points you'll be getting from a Tetris at level 255 might be wrong, even though you wouldn't even notice it with the score capped out at its maximum, but the game won't crash. It's only going to crash if a critical scratch RAM variable is overwritten that has to deal with where the CPU's program counter is going to end up. Which is why the game will crash if this dynamic jump routine is interrupted. But this also explains why it doesn't guarantee a crash. The timing window for where the CPU needs to be interrupted to get a crash is incredibly small. It has to be between this STA and this JMP instruction. This turns out to be only 30 machine cycles, or 16.76 microseconds. So depending on exactly how much work the CPU had to do on this frame will dictate whether or not the game crashes. If there's not enough work to do, this code runs too early in the frame, and the interrupt will happen way after it gets executed. But if there's too much work, the interrupt will occur before this routine even has a chance to run. It has to be exactly just the right amount of work to get the interrupt to fall within this tiny window. Now, this routine actually runs many times throughout the course of a frame of execution, since it is a general purpose routine used for every dynamic jump in the code. However, 8 of those times, this routine runs after the huge score calculation loop we just looked at. So the chances of a crash occurring are effectively multiplied by 8, since interrupting any one of them will crash the game. For a sense of scale, here's the entirety of the code that runs during a single frame when clearing a Tetris on level 29. Here's the part of the code belonging to the score calculation routine, and here's the windows where the interrupt would have to happen to crash the game. And here is approximately how much code ends up running when the interrupt does happen on level 29. All of this is the CPU spinning in one spot. With only 30 iterations of the scoring loop, the interrupt happens well beyond any of these regions. Eventually, the calculation time for adding up the points for a single while leveling up from level 154 to 155 takes just long enough for the interrupt to possibly hit the dynamic jump routine for the first time. This is because, maybe counterintuitively, a single takes the longest to integrate into the score, since it is the only score out of the 5 to have a non-zero digit in the tens place. After that, though, the requirements for getting a crash to occur become very complex. The game can only crash on the single line clear that levels you up to 155. It won't crash within level 155 because the score calculation doesn't take up enough time. It was only the additional work that went into updating the current level that allows it to crash on the first go-through. However, on level 156, the game can crash on any single line clear. On level 163 and onward, though, getting a single will always guarantee too much work for the CPU, and a crash will never happen again. It takes up to level 165 for a Tetris to crash the game, as long as it's on the level up. Level 166 can crash on any Tetris. Level 167 can crash on any triple, and level 168 can crash on any double. Starting on level 177, there's just too much to calculate that any line clear will not result in a crash any longer. There are some weird gaps here, and these are situations where, even though there are enough calculations happening to possibly trigger the crash, it will just never happen because it never exactly lines up perfectly for an interrupt to hit that sensitive subroutine. Each of these situations don't all guarantee a crash either, just that it is possible. This is because there are some things like the music, exact line clear count, tetramino type, and stack height that can cause subtle variations in exactly how much code is being executed in one frame. But then, after a long time, even letting a piece lock without clearing a line can cause a crash. The score updating routine still runs when a line isn't cleared, it just effectively adds 0 during each iteration of the loop. Even without all of the work of clearing out the lines in the board, just calculating the score for such a high level is enough to get that interrupt to happen at the perfect time. This can start happening on level 247 and poses a threat all the way to level 255. If you do manage to clear level 255 while avoiding any crashes, then the level will roll over back to 0, and it's just like you started the game over again. The last thing to look at is the glitchy tiles that appear all over the screen starting on level 160. This is just another case of the interrupt hitting an important routine, but instead of that dynamic jump routine, it's a routine responsible for preparing certain tiles to draw to the screen. The CPU may not be able to access video RAM while the PPU is generating the video signal, but it can prepare a buffer of sorts in work RAM. Then, when VBlank occurs, it can transfer everything from that buffer to VRAM right away to save time during the short period it has access. Part of this processing has to do with preparing objects to draw to the screen. Most of the entire Tetris gameplay screen is made up of the background. The background doesn't move and is pretty much static most of the time. Moving sprites, however, are objects and are treated differently to the background tiles. In NES Tetris, the currently falling tetramino and the next piece indicator are objects. Each of them are made up of 4 individual object tiles. Every frame, the game will look up which tetraminos are to be displayed and figure out how to arrange the 4 tiles for each of the 2 displayed pieces. Even though the 2 pieces look identical, they are handled completely differently. The 7 different tetramino icons in the next piece box are actually part of a bigger family of sprites that also include all of the animations from the ending screens. These sprites are defined in the ROM as a set of object entries, where each tile takes up 4 bytes, these being its X position, Y position, tile number, and attributes such as palette, background priority, and horizontal and vertical flipping. While each of the tetraminos takes up 4 tiles, since these are part of a broader group of generic sprites, the number of tiles isn't strictly defined. Each of the sprites can be any number of tiles, and the list of tiles is then terminated with a single byte hex FF. Each of these sprite definitions are found in ROM, and then there is also a table of pointers that point to the locations of each of these sprites. Starting on level 160, the code responsible for drawing the tetramino in the next piece box may get interrupted by VBlank. Here is what that routine looks like. There is this memory location that holds the ID of the sprite to display in the next piece box. This code reads that ID and turns it into an index to use to read this table of pointers. The 16-bit pointer corresponding to the proper tetramino is copied to a couple of scratch RAM addresses. All of this code copies each of the 4 bytes of the object tile data into the object buffer. The X and Y positions are offset properly so they appear where they are supposed to relative to the entire screen, but the other 2 bytes go directly into the buffer as is. This loop processes 1 tile at a time and will keep going until it runs into a hex FF byte. This is what triggers this branch instruction to break out of the loop. Now, this pointer gets overwritten by the VBlank routine if an interrupt were to happen during this operation. And unlike the dynamic jump code, this window is wide open, so it is very likely, if not almost guaranteed, to happen once you hit level 161. Since the pointer gets corrupted, the data being copied to this object buffer gets corrupted as well. This is why a bunch of glitchy tiles end up all over the screen. And remember, since this loop isn't strictly defined to run a certain number of times, it will keep looping forever and ever until it hits that magical hex FF byte. If there happens to be no hex FF byte in the area around where the corrupted pointer points, then this loop will just never break and endlessly dump garbage to the screen. Now, it's pretty interesting what this pointer ends up being corrupted by. The VBlank routine happens to use both addresses hex A8 and hex A9 for separate purposes. Location hex A8, which normally holds the lower byte of this pointer, is used when the game is updating the tiles that display the player's score to the screen. When it's finished, this scratch RAM will end up holding the highest 2 digits of the score, which will always be 99 at this point, so the lower half of the pointer will always become hex 99. Location hex A9, which normally holds the upper byte of this pointer, is used to temporarily hold the state of the buttons on the controller. So the pointer will be different depending on what buttons are being pressed at the time the score is calculated. Some of the button combinations will create a pointer that points to an area that has a terminator byte, and some of them won't. For example, if you are holding the A button, this creates the pointer hex 8099. This area of ROM does have a hex FF byte, so at some point the loop will read this byte and exit out just fine. If you are holding the down button, this creates the pointer hex 0499. This actually points to RAM and is the area in memory where the state of the entire board is held. This will only ever contain the bytes hex 7B, 7C, and 7D, the 3 tile variants, as well as hex EF for blank spaces. Since there will never be any hex FF bytes here, this will loop infinitely as long as you're holding the down button. Holding the select button is fun because this creates the pointer hex 2099. This area of memory is where the PPU hardware registers are located, so it's possible to really crash the game by doing this. Despite all this, if you just don't hold any buttons down, this makes the pointer hex 0099, which includes an area of RAM where frequently used variables are held. One of these memory locations just happens to be a sort of frame counter which gets incremented once per frame by the VBlank routine. Which means that most of the time the loop will keep going forever, since there are no hex FF terminator bytes in this region. However, every 256 frames, that counter does hit hex FF, and only on that frame will the loop break out and the game will continue normally. In fact, when you do this, you can see that it's the Y position of this glitched tile that takes on the value of that counter. So it will glide across the screen, but the moment it finds its way back inside the next box, the game will continue on like normal. Now that was just the next piece graphic causing the game to hang. If you press select beforehand to disable the next piece from appearing at all, this garbage will never appear since the routine that draws the piece doesn't end up running in the first place. However, starting at level 167, the routine that draws the falling Tetramino will have the opportunity to cause some glitches, and there's no way to disable it. Here is the code that prepares the object tiles for the falling pieces by writing them to the object buffer. Unlike the last code, this code does define a loop to run for a specific number of frames, 4, one for each of the 4 tiles in the piece. It also uses a different format for the object data in the ROM. There are 7 different Tetraminos, but this table also takes care of each orientation of each piece, so there are actually 19 different entries. Each Tetramino is made up of 4 tiles, and each tile has 3 bytes of data associated with it, its X offset, Y offset, and what type of tile it uses. This code takes the Y offset from the data, converts it from tile coordinates to pixel coordinates by multiplying it by 8, adds the Y position of the piece on the screen, and puts it in the buffer. Then it takes the tile number and puts that straight into the buffer. Then it puts the tile attributes, which are hard-coded to 2, and puts that in the buffer. That's why each tile only takes up 3 bytes instead of 4 in the ROM. The next thing it does is double-check the object's Y position. If it's above the top of the board, it will effectively erase it from the screen by setting its tile number to hex FF, a blank tile, and its X position to 0, so that it doesn't appear on top of the background border. Otherwise, it takes the X offset from the ROM data, again converts it from tile coordinates to pixel coordinates, adds the X position of the piece on the screen, and puts it in the buffer. Then the loop counter is decremented, and it jumps back up to the top until it does all 4 tiles. Say, where is that tile counter variable stored in memory? Oh, at address hex A9. That's the same scratch RAM address that got corrupted by the controller buttons in the last code block. If this routine gets interrupted at all, the loop counter gets corrupted and causes it to iterate many more times than it was intended. Because of the way the counter was implemented, it is decremented once before it is checked against to break out of the loop. This means if you are pressing no buttons on the controller, this counter will be corrupted to be 0, and on the first iteration back from being interrupted, the counter rolls around back to 255, and we'll attempt to copy over 256 objects to the buffer on this frame. This of course takes so long that the loop will be interrupted again, where the counter gets recorrupted back to 0, and the same thing happens again, frame after frame. However, if you press any button on the controller, the counter becomes something other than 0, so the loop manages to finish in time without being interrupted again. It turns out that the loop gets interrupted again on its 253rd iteration, so pretty much any button combination, other than pressing every single button at once, will lower the counter just enough that it will be able to finish in time. When the loop counter gets corrupted, the game attempts to draw all 19 Tetramino orientations at once. Not only that, but since there are only 240 bytes in this table, 19 Tetraminos plus one extra that shows up completely blank, times 4 tiles times 3 bytes, when the X index register goes out of bounds all the way to 255, some glitch tiles end up being drawn too. And since 256 is not divisible by 3, the number of bytes assigned to each tile, every time X overflows, the parity switches and the bytes are used for the incorrect purpose, causing even more glitchiness. Now, the NES can only display 64 objects at once, and only 8 of them can be visible on a scan line at a time, so that's why when the game is frozen like this, the graphics start to flicker a bunch. It's only able to display a subset of the total glitched objects at once, and each frame chooses a different subset. I'd like to take a moment to make a huge shout out to HydrantDude for figuring out a lot of the intricacies on how NES Tetris works and what exactly causes the crashes to happen, as well as helping fact check this video. If you're interested about what exact combinations of levels and line clears will result in crashes and their exact probabilities, check out this spreadsheet that is linked in the description. This is an incredibly information-rich document, and it includes a few wonderful visualizations like this one. This document acted as my sanity check for my own research, so I appreciate that a ton. He's also made a few videos of his own about how things work in Tetris, so please check them out on his channel. Thanks, HydrantDude. And also, thank you for watching this video. Retro Game Mechanics Explained is kept afloat thanks to everyone who watches, and especially those who pledge extra via YouTube memberships and Patreon subscriptions. While YouTube ad revenue can be a roller coaster ride, monthly support is more predictable and reliable, and allows the channel to exist without the need of extra means of income like sponsorships. If you'd like to support the channel, consider becoming a patron or member. Even the smallest bit helps out a ton. Thanks again.